Hey, Kim, redox reactions, acidic solutions. Let's do this. Alright, let's discuss the steps first. First step, note the half reactions. The half reactions are oxidation and reduction. The reactants in the oxidation reaction are the ones that are they're losing their electrons to be given to the ones that will be reduced. The ones undergoing the reduction reaction are the reactants that are gaining the electrons lost in the oxidation process. Think of it this way: these things are called redox reactions because you have electrons being given from one set of reactants to another set of reactants. Step 2. Balance the atoms. It's already obvious. Step 3. Balance whatever existing oxygen particles you see with water molecules. It's just simple. Just add water to the other side of the equation. Step 4. Balance whatever existing hydrogens you got from that water with hydrogen protons. It's just for the sake of balancing. Step 5. Balance the charges with their electrons. You basically just need to balance the electrons. Step 6. Balance the electrons used in the half reactions. And step 7 is to add the half reactions together. And then cancel out whatever is going to cancel themselves out. With that out of the way, let's get to an example. Okay, let's go over each step one by one because this is gonna take a while, definitely. Alright, so the first step is to identify the half reactions of oxidation and reduction. As said earlier, oxidation is the reaction that wherein reactants would give up their electrons and just lose them outright. Wherein reduction is just gaining those lost electrons. So after doing some cross-referencing to figure out the charges of the chromium in dichromate, we've come to realize that each chromium atom in the dichromate has a charge of 6 plus. Because to get a net charge of -2, you'd have to have the chromium have a charge of 12 plus which should counteract the oxygen's -14 charge and then just total up to -2. We don't have to worry about the other side. It's just this side that we have to worry about because we didn't know the charges. Anyway, we already know that chlorine has like a charge of -1 because it's already stated. We know that the chromium on the other side has a charge of +3 because that's also noted. And we know that the chlorine gas on the other side is just neutral. With that being said, our oxidation reaction should be chlorine and our reduction reaction should be dichromate and chromium. As seen here. Now we have to balance the atoms. In the case of our oxidation reaction, you can see that we were missing a chlorine atom on the reactant side. So to fix that up, we just added another chlorine atom to compensate. In the case of the reduction, we didn't have enough chromium for the product side, so we just added more chromium there. And now we move on to step 3. Step 3 would be to balance the oxygen with water. Just put whatever water on the other side to match the amount of oxygen on the other side. Think of it this way. We don't really have to worry about oxygen for our oxidation reaction, but we have to do so for our reduction reaction. We have 7 oxygen atoms in dichromate in the reactant side. To counteract that, we have to add 7 molecules of water onto the product side. After which, we need to do step 4, which would be to add the appropriate amount of hydrogen protons to match the amount of water molecules on the product side. considering we added like 7 water molecules, and since there's always 2 hydrogen atoms in a single molecule of water, we just had to add 14 hydrogen protons. Now for step 5, to balance the electrons in the charges within the atoms. In the case of our oxidation reaction, we have to add in the charges that are lost. So in this case, we have like the two chlorine atoms with both having a total charge of 2 electrons. For that to become 0 in the chlorine gas, they need to lose those electrons. So that's already taken care of. With a reduction reaction though, this gets a bit complicated because there's just so many atoms to work with. But long story short, getting the difference of the protons and electrons of the hydrogen and dichromate, we get 12 protons, and to match the 6 protons on the product side, we need to add 6 electrons on the reactant side. As a result, we'd have like 6 electrons on the product side, or should I say reaction side, and we basically have like 6 protons in total. After balancing the electrons in the atoms, we need to move on to step 6, which is to balance the electrons in the reactions. We don't really have to worry about it in the reduction reaction, but our oxidation reaction doesn't need to worry about it though. So basically, just get the greatest common factor of 6, because that is the amount of electrons on the reactant side, because those are being obtained from the oxidation. Considering we need to have 6 electrons in our oxidation reaction, just like in our reduction reaction, we just need to multiply 2 by a number that will make it 6, which is 3. Blah blah blah, math. We get 6 chlorine atoms, and then 3 chlorine gas atoms, and 6 electrons. Step 7 is to just rewrite the entire equation and then just remove anything that would cancel out each other. After putting all the reactants on the reactant side and all the products on the product side, we can just cancel out whatever will cancel themselves out, which in this case would be the electrons. So with that being said, our final answer would be 6 chlorine atoms with a negative charge plus 14 hydrogen atoms, or should I say hydrogen protons, plus the dichromate turned into 3Cl2 plus 2Cr3 plus 7H2O. My god, that is a mouthful. Anyway, this is how you deal with redox reactions. It's very complicated, to say the least. Oh, and by the way, if you want to double check, just double check the total number of electrons on both the reactant and product sides. As you can see, 14 from hydrogen, 6 from chlorine, and 2 from dichromate. You get a sum of 6 electrons, and that's the same amount of electrons on the other side, so that already means it's okay. And so are the amount of atoms, so you don't have to worry about that either. Anyway, this is how complicated the redox reaction is, and this is how it's done. I honestly hope you'll all be able to get this done better than I did. So yes, have fun.